Welcome to IIT PAL special session. So, today we will discuss aldehydes and ketones. So, first we will discuss UPAC nomenclature, and sometimes suppose you have this compound, a ketone. So, if you see the numbering of the longest chain, it comes like this: 1, 2, 3, 4, 5, 6, 7, 8. And now, if you take the double one, then it becomes 6 dash 7 dash. Now, the UPAC nomenclature of this compound will be, so this will come as a substituent. So, you have to consider the longest chain. And here this will be, so 5 group there is a substitution. So, 5 vinyl 2 octanone. Now, if you put a hydroxy group here like this one, one, 2, 3, 4, 5, 6, 7, 8 and 6 dash 7 dash. So, here also this is the longest chain. So, you have to take this one only, and this group is hydroxy ethyl. So, 5 1 hydroxy ethyl, again 2 octanone, or octane 2-one also is okay. Now, if you take this compound, what happens? There are 2 carbonyl group here. So, now you have to take this chain, because here is the ketone group is there. So, this you have to take the numbering now: 1, 2, 3, 4, 5, 6, 7, and this is the substituent. But if you take this side, then what happens? This 5 gets the 5 position, this propyl group comes. Alternatively, if you take from this side, one, 2, 3, 4, 5, 6, 7. Okay, I will draw again. So, yes, now if you take from this side, 1, 2, 3, 4, 5, 6, 7. So, what will be the nomenclature? Because this side it is coming 3 and this side it was coming 5. So, you have to take this side only. So, it will come 3 propyl. Now, this is heptane. So, heptane, now 2 and 6 position keto group is there. So, heptane 2,6 dione. Now, if you take aldehyde this side, so what will be the nomenclature? Now, this aldehyde group is the main group here, and this is the longest chain: 1, 2, 3, 4, 5, 6, 7, 8. So, this is the longest chain, and this side ketone group is there. So, in the chain you do not need the keto group incorporation, because this will be 7. So, here what will be the nomenclature? So, the nomenclature will be 5. So, this is the acetyl group, acetyl. So, this nomenclature will be 5 acetyl, and this is the octanol. So, this is the aldehyde. So, 5 acetyl octanol. Now, we will see some chiral compound. Suppose this compound aldehyde. So, if this is in the racemic, just to tell the relative stereochemistry. So, this is the cyclohexane ring 1, 2, 3, 4. So, trans 4 hydroxy cyclohexane, and one position the aldehyde group is there. So, 1 carbaldehyde. And if this is only the chiral form, then you have to tell this stereochemistry will come 1 R, 4 R, like this, same thing, 4 hydroxy. So, if it is the plus series, only the chiral one enantiomer is there, then it will be like this 1 R, 4 R you have to draw carbaldehyde. Like this one, the methyl group, so I will draw again. CH3, CH. So 1, 2, 3, 4, 5. So aldehyde will get the 1. So what will be this stereochemistry? So this is R, this is also R. So 2 R, 3 R. First we have to give the chirality 2 R, 3 R, 2 ethyl, 3 methyl, pentanal. So this is the UPAC. Now we will discuss the reactivity. Reactivity as you know, carbonyl group is slightly basic. So this is weak base. So if you put acid, what happens? Then this carbonyl groups gets protonated, and this is called activated carbonyl group. Now this activated carbonyl group, here you can react weak nucleophiles, because weak nucleophiles will not react with the parent carbonyl compound, but will react with this activated carbonyl group. Weak nucleophiles like R2OH, that is alcohol, water, and then you can get OH, O2 or OH. So this is called acetals when it is with alcohol, or hydrates, acetal, and with water it is called hydrates. So, we can discuss one example like acetone. If you put H3O plus, so what happens? These groups get protonated. And this is in the resonance form of this. Now, if you put water, that is already water is there, then water will react now to get this one C3. So, there will be positive charge first, and now after H minus liberal, ऑफ है तो ना,
मतलब ये जो पेन है ना सर,
हाँ,
इसका अगर इसमें क्लिक करेंगे तो नेक्स्ट स्लाइड हो जाएगा।
ओके, ठीक है, ठीक है। सो माइनस H प्लस you get the hydrate. Okay, now we will discuss acetals. And cyclic acetals are more stable than acyclic acetals. Like if you react this ketone with ethylene diol in presence of H plus, this you get. So, this is the cyclic acetals, and because of the stability they are acts as a protecting group. So, these cyclic acetals useful as protecting group of aldehydes and ketones. Why? Because acetals will hydrolyze under acidic conditions. But are stable to strong bases and nucleophiles. And they are easily formed also. They are easily formed aldehydes and ketones, and we have already told they are hydrolyzed, so it can be easily deprotected. So these properties are good, and that's why it is called ideal protecting group. So now we will see some application. So many times what happen, if you want to use a reagent having an aldehyde group, and that aldehyde should be protected as acetal, and later it can be deprotected. Like if you want to prepare this one, from cyclohexanone, how you prepare this one. So if you see this one, if you disconnect here, you need a nucleophile and this is electrophile, and you can start from this compound bromo, because you need a nucleophile here, and the obvious is the Grignard one. So if you react this with magnesium, then the aldehyde will react. So what you have to do, first you have to protect this aldehyde group. And now if you put magnesium ether, then you get Grignard one. Now you can react with cyclohexanone. So after reaction with cyclohexanone, and you can do the hydrolysis, you get this product. Similarly, so you can see here aldehyde group, this is ketoaldehyde, and the aldehyde group is untouched, but the ketone group has to be reduced. So that is not possible with known reagents. So what you have to do, you have to protect the aldehyde. So this you have to protect. Now if you reduce with sodium borohydride, and then aqueous hydrolysis, acid hydrolysis, then you get the aldehyde back. So here the acetal production can be done selectively on the aldehyde in presence of ketone. So some more examples of acetals. Like hydrolysis one, it can be questioned that if you do hydrolysis of this one, what will be the product? So, here if you put acid, what happens? H plus 1 oxygen will be protonated, and once the oxygen is protonated, this will open. So, you get oxonium ion here, which now water will attack. So, and initially it will be protonated. So, this water after attack, and then this oxygen has to be protonated. And then you get your diol, plus benzaldehyde. So, this is the question can be asked, that if you do the hydrolysis of these acetals, what you will get? So, you will get benzaldehyde and 1,3-propanediol. Another questions can be asked, that if you do PCC, then H3O plus and then ethanol and acidic condition. So, if you do PCC, PCC oxidize alcohol to aldehyde. So, first you get this one, and now you have two groups, double bonds as well as the aldehyde. So, you can consider the double bond as well as aldehyde both reacts, or we can do stepwise also. This is possible that this double bond reacts and this aldehyde is like this. Also, you can think this product also possible, the aldehyde hydrate is formed and this also forms. So, any mechanism is fine. And then under acid condition what will happen? So, under acid condition this OH will react to the aldehyde, or this will react to the aldehyde hydrate. Here water will eliminate, and here this cyclic compound will form. So, this is hemiacetal. And now, if you put ethanol H plus, so in acidic condition the water will eliminate and you get this one. So, water will eliminate and then ethanol will react . So, this is the acetal. So, another application we can think that so, if you see the product structure, here aldehyde is intact and the double bond has to be diketone. So, double bond we know the KMnO4 alkaline condition, it can give the diol, and then chromium oxidation can give the ketone, but if you put the KMnO4, then the aldehyde will be oxidized. So, you have to first the aldehyde has to be protected. And now you can KMnO4 OH minus, then you get 6 diols 3 plus minus, and PCC oxidation or CrO3 or Jones oxidation CrO3 H plus. And now the aqueous acid, so hydrolysis of the acetal will give you this aldehyde. Another reaction which is also important, that is the acetyl exchange. So, if there is a hydroxy group in the molecule, then it can make intramolecular reaction, and under acidic condition it can exchange. So, one example we can see. So, if you see there is a hydroxy group here and this is the acetal motif. Now, if you put acid, what will happen? So, if you put acid, you see we have already discussed that how it gets protonated and opens the ring. So, it generates a oxonium ion. So, here also it generates first a oxonium ion, so like this protonated. So, oxonium ion is formed and this alcohol is there. So, now 1, 2, 3, 4, 5. So, this intramolecular reaction will happen and you get this compound. After H plus liberation, you get so this oxygen is here. So, this forms the acetal here. So, this is important that you have to be careful that when you have an alcohol in the molecule, then under acidic condition it can do the exchange. Another reaction is this. This is the enol ether. The enol ether, and the question is that H3O plus, what would be the product? We can put a methyl group here. So, enol ether also, if you put H plus, it will react like this. So, earlier we have seen the acetal, but here this conjugation is there. So, a oxonium ion will form here also. Now, water will add here. Now this proton will exchange, so it will go to the methoxy group and so you get ketone first. So you get a ketone. And what happened when ketone is formed, then the acidity of this hydrogen is increased. So this will, under acidic condition, this will be protonated and water will eliminate. So you get this product. So alpha beta unsaturated ketone will form. So aldol and Cannizzaro reactions are also useful reaction. We have already discussed. So now we will see some application and intramolecular version also. So intramolecular aldol, that is also useful reaction. So intramolecular aldol means the two carbonyl group will be in the same molecule, like this one. So this is 1,5 diketone system, or you can nomenclature this 1, 2, 3, 4, 5, 6, 7. So this is 2, 6, F10 dione. Now if you put sodium hydroxide for aldol reaction, what will happen? So you can see that this is a symmetrical molecule and the enolate can form either, so this hydrogen or this hydrogen can be abstracted and makes a negative charge. And now this one, if it generates a negative charge, if 5H plus gets deprotonated, then you get this one. And if 7H plus gets deprotonated, then you get this one. Now if you see this one, now if you want to react here, so 1, 2, 3, 4, this will be 4-member ring. So this is unstable. On the other hand, if you see 1, 2, 3, 4, 5, 6, so here if it reacts, then you get 6-member ring. So this will be the plausible path. And now you get, after reaction, after this attack, you get this one. So a 6-member ring will form O minus. This is suppose 1, 2, 3, 4, 5, 6, 7. So you see this is the 7, is 6, 5, 4, 3, 2, 1. So this 2 becomes now a quaternary center, and now this is the aldol product after water treatment. This is the aldol, and if you heat it, then the the dehydration will happen and you get the alpha beta unsaturated ketone. So this is 1,5 keto systems. Now we can discuss 1,4 keto system also. So, suppose this one. So, this is 1, 2, 3, 4, 5, 6. So, 2, 5. Two 5 hexane dione. So, here if you put the sodium hydroxide here, this will get deprotonated here also, because this will generate a 3-member ring, but this will generate a 5-member ring, and similarly you get this compound. So, this O minus, then H2, then this. So, 5-member ring will form. Now, if you put one cycle, that already cyclic compound is there with a diketo system like this one. So, here also this is 1 5, 1 2 3 4 5, and this is 10-member ring. So, we can give the numbering like 1 2 3 4 5 6 7 8 9 10. And now, if you put sodium hydroxide, what will be the product? Like last time we have seen the acyclic case, the 6-member ring form. Here also the 6 hydrogen will be deprotonated and this will react to the carbonyl group, and this becomes a 6-member ring and this also 6-member ring. So, this is quite stable. So, 2 6-member ring will form. And this is the orange. So, 1 2 3 4 5 6 7 8 9 10. So, this is the 1 carbon comes here now, and this 5 position carbonyl group. So, now if you heat it, so the aldol condensation product will form. So, you get this. Enone. So, another reaction that we want to discuss, the Cannizzaro reaction. That we know that this is a redox reaction. And carbonyl groups, carbonyl compounds having no alpha hydrogen will react, and also strong base is required. So, one question that came few years back, that if you put acetaldehyde and 4 equivalent formaldehyde under basic conditions, that is KOH condition, what will be the product? So, if you see the acetaldehyde, there are 3 alpha hydrogen is there and 4 equivalent of formaldehyde is there. So, 3 equivalent will participate in the aldol reaction and last equivalent will participate in the Cannizzaro reaction. So, at first you get this one molecule reacts, then another molecule comes, now if you see this one here, there is no alpha hydrogen, this is quaternary center, no alpha hydrogen, and now the Cannizzaro reaction will happen. And since formaldehyde is a small aldehyde and it does not have steric repulsion, so it is mainly acts as donor. So, hydride will delivery will take place. So, sodium hydroxide will react with this. Then you get this. So, this hydride. So, you get this is the product CH2OH. So, this CH2OH came from Cannizzaro and another 3 came from the Aldol. So, this is the symmetrical molecule. Another reaction that you have studied, that is the halogenation. So, we will discuss one example of bromination. So, what happens, suppose if you see this ketone, this after base you can generate a nucleophile here. So, this is nucleophilic center, but when you put acid and bromine condition, suppose 1 equivalent, then you get this. So, this center now electrophilic center. So, earlier this one was a nucleophilic, now it is electrophilic, and now you can do many nucleophiles, you can react in this position, like if you react with this amine, dimethyl amine, then you get this compound. Because dimethylamine does not react with the carbonyl, because this is the more reactive here, and you get this. Now, the question is how to get this compound. In this case, you have to disconnect here and minus plus if you do, then you get and if you put a plus, plus is actually double bond you can put, and this is the iminium ion. And under basic condition if you react acetophenone and in this iminium ion, then you can get this bond. So, this is Mannich reaction. Okay, now at last we will discuss ozonolysis. So, ozonolysis of polyenes is very important. Ozonolysis of polyenes, that we will discuss with some examples. Suppose if you do the ozonolysis and then the reductive workup, zinc acid you can give also, acetic acid. So, what will be the product? So, you can see there are 3 double bonds here, 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 and ozonolysis means you have to, the double bond you have to displace by 2 carbonyl groups. So, if you give the carbonyl groups here, now you can see here 1 carbonyl and here 1 carbonyl. So, this is aldehyde, ketone, and now 1 carbonyl will come here. So, there will be total 3 molecules. So, this is 1 molecule. So, another this side aldehyde will come, this side again ketone and formaldehyde. So, if you react polyene under ozonolysis condition, you get many carbonyl compounds. So, this is useful reactions and we can discuss some problems. So, the problem is that beta myrcene has no triple bond. So, only double bond is there and its molecular formula is C10H16, and when treated with platinum 2,6-dimethyl octane is formed. So, this is the 2,6-dimethyl octane. This side 1, 2, 3, 4, 5, 6, 7, 8. So, this is the 2,6-dimethyl octane is formed. Now, when it is treated with ozone, treatment with ozone followed by acidic zinc workup. A is formed, A is C5H6O3 acetone and 2 equivalents formaldehyde. So, the question is what is the structure of methine, beta methine. So, you can see this framework is this. Now, you have to put double bond. So, what will be the degree of unsaturation? So, first you have to calculate the how many double bonds will be present. So, if you see this normal 10 carbon here. So, this will be the C10H22 10H minus, so degree of minus C10H16 6 hydrogen. So, H6 and you have to divide by 2. So, 6 by 2 is equal to 3. So, 3 double bonds will be present because this is the completely saturated system. C10H22 is the 2,6 dimethyl octane, and the unsaturation you have to calculate that how many hydrogen divided by 2. So, there are 6 hydrogen is coming. So, 1 double bond liberates 2 hydrogen when it is formed. So, there are 3 double bonds are present, and now you can see this is the 2 equivalents of formaldehyde. So, 2 equivalents of formaldehyde means the terminal. So, this means the terminal methyl group should be considered here. And if you see the acetone structure, so this is the acetone. So, acetone you can see this can come from this one, because here the motif is there, acetone motif, because here if you see this acetone will not come. So, most likely there will be a double bond. So, there is a double bond here. Now, if you consider that 2 equivalents of formaldehyde will form. So, formaldehyde will form only from the terminal one. So, here now once you put a double bond, so you have to put a double bond here, because this will give formaldehyde, and also here because this will give a formaldehyde. So, this will be the structure of the beta methine. And now, what will be the structure of A? So, this will be beta methine, and structure of A will be, so if you do the hydrolysis here, you get the aldehyde, here you get aldehyde, a keto, and here you get aldehyde. So, this is A, C5H6O3. So, this is A and this is beta methine. So, you have to see the small fraction first. So, acetone you can see this fragment can generate from here, and formaldehyde from the terminal methyl groups only. So, in the terminal position you have to put the double bond, and here you have to put a double bond. So, we can discuss another problem. So, this is also C10H6, H16. So, this is A, and now it reacts with H2 platinum, it generates B. When A is treated with ozone, acidic zinc, compound C, and another product. So, the question is what is the structure? Okay, the structures are given. So, B structure is given. So, this is B. So, this is B. B structure is given, and also C structure is given. So, C structure is this. So, this is the C. So, this is the complete framework here. Now, you have to put the double bond. So, here it is written that it does not, when it is reacted with KMnO4, it gives brown precipitate, KMnO4 O minus. So, brown precipitate of MnO2. So, that means the double bonds are present. So, unsaturation here also you have to calculate. So, here also the unsaturation degree of unsaturation. So, similarly C10H22 minus C10H16 is equal to H6, and that means 6 by 2 is equal to 3. Now, structure of B is given. So, B contains one cycle. So, this cycle is a one unsaturation. So, number of double bonds will be 3 minus 1. So, this is with the cycle. So, 2. So, 2 double bonds are present and this is the main aldehyde components are coming. So, if you see this one, here you see this 1, 2, 3, 4. So, this is the 4 coming, and this 1, 2, 3, 4, 5, 6. So, if you connect 1 and 6, then you get a nice 6 member ring. So, first you have to connect 1 and 6. So, if you connect 1 and 6, what happens? So, the alkene will be like this and this. So, here we connect it, now this one. So, this is the 1, 2, 3, 4, 5, 6. So, what happens? This 1 and 6, here if you put the double bond under ozonolysis, it will give this. Now, this is the carbonyl group here, and if you put a double bond here, then the framework will be ready. So, the A structure is, so structure of A is this, because you have to put a double bond, one carbon you have to bring. So, C is this and another product. So, if you do the ozonolysis here, this will remain here, it will dead, but here if you terminal double bond, we have seen the formaldehyde will form. So, another compound will be formaldehyde. Now, we discuss some common examples of reductions, oxidation. So, this aldehyde group can be converted to the alkane, and we know these conditions. So, A is zinc, This is the Clemenson condition, zinc amalgam, HCl. This is acid condition. Basic condition, the Wolff-Kishner that we know. Now the reduction we know, sodium borohydride or lithium aluminum hydride, and D will be, so here you have to put a tosyl group, tosyl chloride pyridine, and then the OH group can be removed to the alkane, then lithium aluminum hydride or sodium borohydride. Another is this so these are not equilibrium, just the transformations. Alcohol to aldehyde, say acid, the secondary alcohol, is same, the BC oxidation here is happening. From acid to ketone, from acid chloride to ketone. So what will be A? This is Rosenbaum condition, H2 palladium BaSO4. What will be B? B can be PCC. What will be C? C will be lithium aluminum hydride or sodium borohydride. What will be D? So D, draw again. So A will be hydrogen palladium sulfate, palladium BaSO4, sorry, palladium BaSO4. B will be PCC, C will be lithium aluminum hydride or sodium borohydride, D will be silver oxide or H2CrO4, oxidation. What will be E? E will be SOCl2, acid chloride you can write. F will be R-MgBr, then acidic workup. What will be G? G will be 2 equivalent R-Li, then H3. And what would be the H? H you can put cuprate or cadmium. So cuprate is the most popular. So thank you.